Ladies and gentlemen, dear fellow South Africans, welcome to this talk on the biogenic origin of Witwatersrand gold. But before I start with my talk, let me express an apology. Unfortunately, unforeseen circumstances prevent me from giving this talk in the planned way, that is, as a real-time online Zoom conference. So I have to resort to this plan B and give you now a pre-recorded version of my talk. I hope you don't mind too much, and I sincerely hope that you can still take home some kind of message from this nevertheless. Well, this is part of a series of talks on South Africa's geoheritage. And surely there's one geological heritage that has shaped South Africa's economy and society probably more than any other, and that's the Wits goldfields. So in this talk, I want to focus on the ultimate beginning of this geoheritage, and I will try to show you that without the fortuitous combination of the evolution of the early atmosphere, hydrosphere, and last but not least, the biosphere, there would be no Witwatersrand gold. Well, you all know that South Africa has been the leading gold producer in the world, and for most of last century, about 2/3 of the global gold production came from South Africa. However, over the last couple of decades, there has been now a widening gap developing between South Africa's gold production and the global gold production. If you want to have a look into the future, we can play a few games. A simple one would be applying just a simple Hubbard linearization to the South African gold production. And that's on the lower diagram, where we plot the annual production divided by the cumulated production. And we plot this against the total cumulative production. And in a mature production cycle, you develop a more or less linear trend here, and we can extrapolate this trend towards the x-axis, and at that intersection we should reach the total amount that can actually be extracted from a given, whatever commodity from whatever source, and in this case, of course, the gold from the Wits goldfields. Now, the theoretical value for this would be 56,000 tons of gold. Comparing this with, I don't know the exact number today, but I guess it would be somewhere around 53,000 tons of gold. You can see there's not that much left over. So effectively, this shows that the production cycle of the Witwatersrand gold mines is extremely mature, and there's an era that is slowly but surely coming to an end. Now, unfortunately, but typical of many famous big metallogenic provinces in the world, we only understand the genesis of this ore province at a time when the production is coming to, as I said, a very mature stage. And that's really what I would like to talk to you about today, our current understanding of how the Witwatersrand gold actually formed. Now, this is a topic that has been on the cards for more than a century, and I dare say that anything that the geo-imagination of any geologist can dream of has been suggested as a possible genetic explanation for the Witwatersrand gold. There's, of course, the idea that the gold is a placer gold, but there was early ideas already about an epigenetic origin, initially in terms of a magmatic origin. There have been various metamorphic models suggested, sedimentary exhalative models have been suggested. Some people even related it to the Vredefort impact. There were already quite a number of years ago first ideas that maybe microbes had a role to play in the evolution of these goldfields. There were all sorts of very strange ideas, and I don't want to dwell too much on this. All I want to say here is that, as I said, almost anything that is imaginable in terms of genetic model has been suggested at one stage or the other to explain these huge goldfields. In the last couple of decades, I think it is fair to say that the big conflict, and it has been a seriously big conflict, some people considered it the most debated issue in the history of economic geology, revolved essentially about syngenetic versus epigenetic models. So this is really sort of the story of the 1990s and maybe early 2000s. And most of you here who listen to this, I suspect, will remember that essentially the debate was between modified paleoplacerists and hydrothermalists. And the hydrothermalists, they argued that if you look down a microscope, you see the gold usually positioned in paragenetically late textural positions, as you can see on the top left, where you have clearly nice euhedral pyrite. So that's clearly epigenetic pyrite, and the gold is sitting here as inclusion in this pyrite. So this gold must be late. That cannot be a syndepositional gold. There's no doubt about that. On the other hand, this famous specimen from the basal reef with this very nice sedimentary features here, nice cross-bedded with nice bottom set and foresets, and all these heavy mineral concentrates are effectively defined by gold particles. And an observation like this, of course, well, this is of course a sedimentary gold. So the debate revolved essentially around the scale at which we looked at the problem. And on the micro scale, everything looked pretty much in favor of a hydrothermal origin. On the macro scale, and that's what the miners used and still use underground every day, following very specific stratigraphic units. So this very strong stratiform nature of the ore bodies has been, of course, used as argument for a syngenetic formation of these gold deposits. So this is the old debate. For those of you who are maybe not that familiar with the Witwatersrand, and especially also for the younger ones amongst you, let me just briefly summarize the main geological features that characterize the gold fields. Because just based on these geological observations, without any fancy geochemical and isotopic analysis, we can already draw some very important conclusions about the genesis of the Witwatersrand gold. So first of all, let's remember that the Witwatersrand gold is strictly controlled by its host rocks. We have very specific host rocks, very specific sedimentary units that host the gold, and these are usually conglomerates. So we have an extreme case of a strata-bound and stratiform style of mineralization. Just as an example, the main reef carrying more than 40 grams per ton of gold could be followed over more than 40 kilometers along strike. So that's a very, very special phenomenon. Some of the gold-bearing conglomerates can be correlated across the Witwatersrand basin over more than 300 kilometers. There is a very sharp contact between footwall and hanging wall and the actual ore bodies. So the boundary of the ore bodies is a sharp boundary in most cases, where the gold grade changes by up to 3 orders of magnitude. So in the footwall and in the hanging wall, we have gold values that are pretty much normal Clark values. That corresponds pretty much to the background gold values. As opposed to several grams to tens of grams per ton of gold in the actual ore bodies. Another important feature is that, yes, there are plenty of cross-cutting features, quartz veins, faults, dikes, all sorts of things. But typically, these cross-cutting features have a much lower gold grade, or none, compared to the conglomerates that they cut across. So in other words, the gold grade in these cross-cutting features is, can be explained by mobilization of gold out of the conglomerates into these, cross-cutting quartz veins, for example, but it's not the other way around. Everybody who has ever mined Witwatersrand gold will confirm that there's a strong correlation of gold with sedimentary facies. Now, there are 2 particular sedimentary facies types that stand out as being particularly rich in gold. Those are fluvial channels and sheet-like conglomerate bodies, which can be interpreted as deposits on wind-blown degradation surfaces. So these are the 2 most outstanding facies in terms of gold grade. On a larger scale, just look at the distribution, at the spatial distribution here of the gold fields. They're all located along the margins of the Central Rand Basin. And then we have, of course, the Ventostope Contact Reef, the VCR, as an important ore body. But the fact that within the Central Rand group we find gold only around the margin, that alone tells us something, that the sedimentary facies along that margin was particularly prone to be mineralized with gold. As far as the VCR is concerned, let's bear in mind that the VCR is rich in gold only in those areas where the VCR is underlain by gold-bearing Central Rand group sedimentary rocks. And a further aspect that shouldn't be forgotten is, yes, all these areas in the different gold fields have experienced variable degrees, variable styles of deformation. But, and that's the important thing, the gold endowment seems to be entirely independent of the style of deformation up here in the northeast or in the northwest or in the southwest. So it doesn't matter how these rocks were deformed, it doesn't matter in which way they were deformed, it doesn't matter to which extent they were deformed. The gold grade, the gold endowment of these gold fields is not dependent on the style of deformation. So deformation was clearly not a first order controlling factor on the gold endowment. Well, this slide I would really like to dedicate to my former colleague Laurie Minter. And Laurie, I don't know, maybe you're listening to this story somewhere. If you are, then just accept my hello sent out to you. Laurie Minter probably changed the scene more than anybody else in our understanding of the Witwatersrand gold, and a particularly important role was played by this very, very famous sample in the meantime, this cross-bedded gold sample, because that was the sample that Laurie took apart by dissolving it in hydrofluoric acid and getting thousands of gold grains out of this sample and then measuring these gold grains and describing them under the SCM. And this has all been quite a few years ago, so forgive me if I show you here an old slide, but this was a very important study because it revealed two things. The study revealed, on the one hand, the presence of morphological forms that are clearly indicative of a detrital origin of these gold grains. Overfolded rims of toroidal shaped or disc-shaped, rounded gold micronuggets. But the other important message was that in the same sample we found not only these micronuggets, as shown here, but also irregularly shaped gold that is clearly secondary hydrothermal in origin, and all within the same sample, within a distance of a few micrometers to millimeters. So this sample effectively provided the best evidence for the famous modified paleoplacer model, hydrothermally modified paleoplacer model. Unfortunately, quite a number of people didn't really believe the story at that time and came up with all sorts of arguments why this interpretation is wrong. I remember having been confronted with arguments such as, these gold forms that we described, they don't really exist, they are artifacts of the sample preparation. Well, it was a bit of a strange argument, but it's true that what you see here on these SEM pictures is not in situ. It's something that has been taken out of the sample. Now, a few decades later, technology makes it possible now to look directly into a sample and study the morphology of gold in such a conglomerate directly in situ. Now, the method I'm talking about is called micro-XRD computed tomography. And that's exactly the same sample that we restudied only a few years ago with a very fancy micro-XRD CT machine. And all you see here is just the gold particles as they occur in this cross-bedded sample. So you're looking here at the bottom set and two foresets, and we will just try to see whether this video is going to work. Yes. So that's the 3D distribution of the gold in this particular specimen. And what you can see very nicely here is that the individual gold particles, they are not connected with each other. These are really discrete, rounded, shaped particles. This kind of spatial distribution cannot be explained by hydrothermal solutions infiltrating a rock and leaving behind some gold. There is no doubt that this gold is essentially, at least as far as the larger grains are concerned, placer gold, detrital gold that got entrapped here in these conglomerates. So I hope that with this little video I convinced you that much of the Witwatersrand gold is indeed placer gold, and consequently it must be syngenetic. But having said this, well, that's a nice conclusion, and it's not something that is terribly new. A lot of people and everybody who is, as I said, actively mined in the Wits mines would concede that, well, that's the basis of day-to-day exploration, the syngenetic model. But it raises a big question, and that's a question that remained unanswered for many decades. If this gold is indeed detrital, as I hope I could convince you of here with this little video, if it is detrital, then the question is, where does all this gold come from? What's the source of estimated 90,000 tons of detrital gold? And this source question, that's really at the heart of my presentation here today. Now, before discussing the potential sources of all the detrital gold, it might be helpful to have a closer look at the relative gold content in the various reefs, and by reef, of course, we mean conglomerates that are rich in gold over time. And on this diagram, I plot not only the Witwatersrand reefs, but also gold-bearing conglomerates from other cratons in the world. But the overall picture that emerges is that, and that's quite important, I think, for the whole story, is that prior to 2.9 billion years, there's hardly anything. Effectively, the Westrand group, which is an age between 2.9 and almost 3 billion years, doesn't contain much gold. Even in other parts of the world, if you have conglomerates that are older than 2.9 billion years, then they usually don't carry much gold. But then, around 2.9 billion years, we get this mega peak. By far, most of the gold in any conglomerate of that age, anywhere in the world, is sitting in conglomerates of 2.9 billion years. Here in the Witwatersrand, these are the main reefs, the carbon leader, the nigel reefs, all those very rich ore bodies at the bottom of the central rand group. And then, as the age becomes younger and younger, the gold endowment becomes less and less. So in a sense, the black stippled line illustrates an exponential decrease in the overall gold endowment of these conglomerates with time. Similarly, the gold grade also decreases exponentially. The highest grades have been achieved in these main reefs and carbon leader and so on at the bottom of the central rand group, 2.9 billion years. And then the grade decreases as the age decreases. So I think there is a very important message hidden in this, and that is something special must have happened around 2.8, 2.9 billion years. This is also a big gold peak. That's a gold mega event on a global scale. And for some reason, this gold was not available earlier on, prior to 2.9 billion years. And for some other reason, this gold trapping mechanism became less and less efficient as time progressed in Earth's history. So what could be the source of this 2.9 billion year placer gold? One model that has been ventilated, especially in the 1980s, were the HAGs, the hydrothermally altered granites. Well, this source very quickly disappeared again from the scene when people realized that the alteration of these granites was actually younger than the Witwatersrand gold. So that cannot be the source. Some people suggested syndepositional exhalites, pyrite-rich, sulfate-rich exhalites along the basin margin. Well, it's a good idea, but we don't have any direct evidence for these X halides. And if we draw analogs to more modern examples, we would expect much more base metals, for instance. So the metal association also doesn't really fit into this X halide model, for which we have no direct geological evidence whatsoever in the Witwatersrand. So that leaves the third option, and maybe that's the option that has been most popular to explain the source of all this placer gold. Again, by analogy with modern placers, recent placers, most of them are derived from some kind of orogenic gold deposits. And of course in the Archean we have a lot of orogenic gold in the greenstone belts. So some erosion of a kind of Barberton type gold deposit maybe could have led to the detrital gold in the Wits. However, there are lots of reasons that speak against such an orogenic derivation, and I would like to dwell a little bit on this topic now for the next few minutes. So, hydrothermally altered granites are out of the question. Syndepositional pyritic X halides are also not an option. So let's talk about the orogenic. And for this discussion, again, it's useful to have a look at the temporal distribution of the gold deposits, especially when it comes to orogenic type gold deposits in comparison with conglomerate hosted, or what we call here the Witwatersrand type gold deposits. The upper and the lower diagrams here are essentially the same, they only differ in the scale. So in yellow, you have the distribution of Witwatersrand type gold, conglomerate hosted gold, and of course there's this huge peak here at 2.9 billion years. That's essentially the gold that is sitting in the central rand group. Then we have a little bit of gold in the Ventusturp conflict reef, 2.7, 2.8 billion years, and then from there on there's not much coming anymore. Orogenic gold, these are the gray bars. We have a whole bunch of peaks. They correspond, we know pretty well, to times of particularly intense orogenic activity, hence the term orogenic gold. And these times of intense orogenic activity are reflected here by the number of detrital zircon, uranium lead ages, so that's this red curve here. And there's a reasonable correlation between the peaks in the red curve and the peaks in orogenic gold down here. Now, this is all pretty much well-known story, but the point I would like to emphasize here is, what about orogenic gold older than 2.9 billion years? Well, there's this tiny little blip here. That's the Barberton gold, 300 tons of gold maybe, but that's not really significant in comparison to the huge amounts of Mesoarchaean detrital gold. So just based on a simple mass balance, there's no way that we can explain the huge amounts of detrital gold, 2.9 billion years in age, from pre-existing orogenic gold deposits, because they obviously didn't exist, or at least we don't know about them. Another potential source could have been, of course, erosion of porphyry gold systems, epithermal gold systems, but there's the same problem. The oldest known porphyry gold or epithermal gold system I'm aware of would be the Cote deposit in Canada, and that's about 2.74 billion years old. And the same would apply to Boddington, probably in Western Australia. So again, we don't have porphyry or epithermal gold deposits that are older than 2.9 billion years. So effectively, none of these classical, in today's world, rich gold sources, orogenic gold porphyry systems, none of them existed at the time when the detrital gold came into the Witwatersrand. So just based on that alone, I think orogenic gold is not an option as a source for the Wits gold. You could take this question, of course, one step further and think about, why do we have so little orogenic gold prior to 2.75 billion years? And a lot of people would have said, well, it's just because either we haven't discovered them yet, or these old rocks have just been eroded, so they're not there anymore. This is maybe part of the answer, but I'm sure it's not the full answer. I think there's another issue, and that is that the conditions weren't simply right for the formation of these kinds of deposits, of gold deposits. Because let's bear in mind, orogenic, intrusion-related, porphyry gold, epithermal gold, all of these types of gold deposits, they form above subduction zones. But did we have subduction prior to 3 billion years? Well, probably not. So this whole issue of potential source hinges on our understanding of the onset of plate tectonics. Plate tectonics help, of course, to change the composition of the subcontinental lithospheric mantle. We need to fertilize the subcontinental lithospheric mantle in order to get good metallogenetic provinces on top of it. And to do this, we usually need to oxidize the subcontinental lithospheric mantle. Now, this oxidation of this portion of the mantle can take place through a series of different agents. One of them would be H2O and CO2. They're not very efficient, and especially in the Archean, well, probably our spreading rates, and if we had subduction, then the subduction rates would have been too fast to really hydrate and carbonate oceanic crust sufficiently in order to make these components here as really effective for oxidation of the subcontinental lithospheric mantle. Another option would be iron 3+, but well, we know pretty well that until the great oxidation event around 2.4 billion years ago, there was not much iron 3+ around, which leaves us with the various sulfuric species. And oxidized sulfuric species were interestingly also not much available in the time window between 3.4 and 2.75 billion years. That's something we know from sulfur isotope studies. So effectively, the conditions prior to 2.75, the conditions were not right for great oxidation of subcontinental lithospheric mantle, and consequently, the conditions were not right to actually form orogenic or porphyry or epithermal gold deposits, and consequently, these kind of gold deposits could not have been the source of the Witwatersrand gold. Okay, so now we killed the orogenic deposits as a potential source. We are left with option number 4. That is that we don't have discrete point sources in the hinterland in the form of nice rich gold deposits that have been eroded to form the detrital nuggets in the widths, but instead we can assume mobilization of background gold concentrations somewhere in the hinterland. And large-scale mobilization of background gold from the hinterland could be achieved by 2 ways. The one is by metamorphic fluids, and the other one is by syndepositional surface waters. Now, metamorphic fluids, that of course would imply an epigenetic model for the widths, and I've just tried to convince you that an epigenetic model is not on. So that's not an option either. And consequently, we're actually left with this last model, and that is mobilization of background gold from the hinterland by syndepositional surface waters. To explain this, I would like to invite you now on a little journey back into the Mesoarchaean. Just close your eyes and imagine what the world might have looked like in the Mesoarchaean. You would have been now in a world in which a lot of CO2 was produced, thanks to a hell of a lot of volcanic degassing. That, of course, led to the lack of carbonates, because the CO2 production would have been much more effective and intense than silicate weathering. And, well, there are no carbonates to speak of in the Witwatersrand sequences. The next thing you should imagine is the atmosphere you're breathing in doesn't contain any oxygen. We know that from the presence of detrital pyrite and detrital uraninite, amongst other things. Imagine it rains. Well, what comes out of these Archean clouds would be like vinegar, because it would have a pH of around 4. And such acid rain would invariably trigger very intense chemical weathering. This intense chemical weathering would attack for instance, feldspars. That would neutralize the pH on the ground surface to almost neutral conditions. Under these chemical conditions, bearing in mind that detrital pyrite is very happy in these Archean conglomerates, we can estimate what their H2S fugacity must have been. And under all these conditions that we can sort of more or less well constrain, we can calculate thermodynamically what the solubility of gold would be essentially as some kind of gold sulfide complex. And the solubility of gold would have been 4 orders of magnitude higher than in the modern world. So in other words, in the Archean we can assume that we had a tremendous high flux of gold through river waters, meteoric waters of the Archean land surfaces. Now there is a beautiful source of gold, because now we are leaching the entire Archean land surface. Do we have any evidence of this? Well, I believe yes. Evidence of acid rain comes from the widespread occurrence of pyrophyllite, and although some of this pyrophyllite is hydrothermal, admittedly, most of it is actually concentrated below old paleo surfaces. So if you do chemical index of alteration measurements across unconformities or erosion surfaces in the widths, then you typically observe that in the footwall there's a decrease in the CIA as you go further down, and then comes a sharp boundary, and then it starts up again until you reach the next erosion surface, and the story repeats itself again. So in other words, a footwall has high CIA values. That means intense chemical weathering subsequent to the erosion of an erosion surface marked now today by conglomerates. So much of the geochemistry of the arenitic fractions of the sandstones, also the sand in the conglomerates, points towards intense chemical weathering. So with the movement from average continental crustal conditions up here into these domains on the ACK diagram. So loss of alkalis, loss of calcium, typical intense chemical weathering. These compositions here, they clearly have nothing to do with chemical weathering. That's hydrothermal alteration, but these compositions are actually restricted to the conglomerate beads, not to the footwall or the hanging wall. A similar picture emerges if you look at the geochemistry of the argillites. Much of it suggests, especially in the central rand group, that we are dealing with high CIA values, high intense chemical weathering in the hinterland, but also within the stratigraphic sequence beneath old erosion surfaces. So if you have this high flux of gold off the Archean land surface, then well, the next question is, how do we get the gold out? How can we concentrate it? There are various ways. In a normal activity diagram where we plot oxygen fugacity versus pH, that's well known from lots of experiments on this system. We know where the maximum gold solubility is, and we also know the contours of same gold solubility. So effectively, if you go into this diagram, maximum gold solubility would be here under these conditions. And you can see, well, you can change anything. Yeah? You can change the pH in this direction, and you reduce gold solubility. In other words, you trigger precipitation. You can go in that direction. You could also go upwards. Now, if you go upwards, you only need just a tiny little bit of change in oxygen fugacity, and you have a few orders of magnitude change in the solubility of gold. This seems to be the most effective way of doing it. Now, when I thought about this a couple of years ago, I must admit I liked this idea of increasing oxygen fugacity, more or less independent. At the same time, Chris Heinrich at the ETH thought about the same problem. He suggested a decrease in oxygen fugacity because that would be a very nice trap, analogous to what we can observe in the modern world to precipitate gold. But the reason why I preferred the increase in oxygen fugacity as trapping mechanism, pretty much following this equation up here, is simply because overall the world was reducing. And what you want to change something is a change to the surrounding system. So in a reducing world, a little bit of oxygen can actually trigger very easily the kind of gold precipitation reaction that is written up there on the slide. But where should that oxygen come from in the Archean world? Maybe from the first microbes that emerged, from the first photosynthesis recorded in Earth's history. But when photosynthesis really started, we don't really know. But we know one thing, and that is that long before the great oxidation event, the first attempts of photosynthesis were made by early microbes. We have evidence of this from polyisotope data on manganese oxides. We have evidence for this based on cerium anomalies in Archean limestones, from chromium isotopes, from all sorts of other redox-sensitive metal distributions. So a whole bunch of independent studies revealed that what we very often referred to as the first whiffs of oxygen. So this first little bit of oxygen produced by this first photosynthesis, oxygenic photosynthesis driving microbes, that these first whiffs of oxygen took place several hundreds of millions of years already prior to the great oxidation event here, possibly as early as 3.2 billion years. So with the age of the Witwatersrand here at about 2.9, we could expect that we had already some microbes that were producing oxygen in the overall reducing Archean world. Evidence of the existence of such microbes is admittedly circumstantial, but some of this circumstantial evidence does exist indeed. And I'm referring to beautiful microbial structures described by the group around Chris Heubeck a couple of years ago from the Moodies group. Now, the Moodies group in the Barberton is 3.2 billion years old, and what the Heubeck group described were these little structures here. Everything that's black here is biogenic carbon, and these little structures resemble in their shape perfectly modern cyanobacteria. So here you've got a recent example of cyanobacteria. You can even see here on this modern example, these little bubbles, these gas bubbles on the top of this structure. These are the oxygen bubbles released by the cyanobacterium conducting its photosynthetic processes. So here on the top, a cross-section through the surface covered by slimy cyanobacteria. And, well, I guess the similarity is given, but that's all we have. And whether these 3.2 billion year old microbes were already producing oxygen or were driving on another metabolic pathway, we don't know. But at least, yeah, there's a similarity to modern cyanobacteria. Just a few more pictures to illustrate what modern cyanobacteria do and how they grow towards the top, how they're even drawn to the top by these rising oxygen bubbles. Because that's a structure I will come back to now in a second with the next slide. Do we have any evidence of such microbes in the Witwatersrand? Oh yes, we have. Plenty of them. Remember the famous carbon seams. Again, the younger ones amongst you, you're in the unfortunate position that you actually have to go into museum collections to see the best examples, because most of these carbon seams have been mined out. But the carbon seams were famous for being particularly rich in gold. In some of the reefs, up to 50% of the entire gold content was bound to these carbon seams. And the carbon seams have been a widespread phenomenon, especially in the lower Central Rand group, on old erosion surfaces ranging in age from about 2.9 to 2.87 billion years. So, what are these carbon seams? Again, the same debate as on the gold and on the pyrite and on many other ore constituents has raged around the source of the carbon seams. Some of them explained them as bitumen, Some of them explained them as kerogen. What's the difference? Kerogen would be something in situ directly derived from some kind of biomass. Bitumen is of course something epigenetic, would be migrating oil solidifying to pyrobitumen. And again, I don't want to go into the details here, I just want to mention here the possibly most important argument, and that is the organic chemistry, especially the isotopic composition of the various alkanes, speaks a very clear language. There is no carbon isotopic fractionation to be observed between the various alkanes in this organic material. And that is a very strong argument against bitumen, because in the case of bitumen, you would have a strong carbon isotope fractionation. So that's the chemical argument. There are a whole bunch of textual and structural arguments I could provide you with that speak for an in situ origin of these kerogen mats or kerogen seams. In other words, they represent old microbial mats. And I don't think it's a coincidence that these microbial mats are so particularly rich in gold. Now, the columnar texture of these carbon seams does even remind one a little bit of these columnar structures or microstructures that I showed you earlier on for the recent cyanobacteria. One can, of course, all of this organic material has been overprinted by low-grade metamorphism and deformation, and that changed, of course, a little bit the organic chemistry and probably also the texture. So I admit that this is circumstantial evidence, but what remains is the evidence that these carbon seams are former microbial mats and that they are particularly rich in gold. Now, completely independent evidence for a very gold-rich meteoric water system or a gold-rich shallow hydrosphere in the Mesoarchaean days comes from pyrite chemistry. From all the many Archaean conglomerates that occur all over the world, I mean, the Witwatersrand is not something unique in terms of the style of sedimentation and mineralization. We find them on all cratons. And everywhere, wherever we go to, irrespective whether these rocks have seen metamorphic overprint or not, we find different types of pyrite. We find rounded detrital pyrite derived from a whole bunch of different sources. We find an early diagenetic pyrite, which is this sort of concentrically laminated pyrite. And we find clearly epigenetic pyrite, as I've shown you already in a previous picture. Particularly interesting are these concentrically laminated pyrites because they are very rich in a whole bunch of trace elements, including gold. And that has been confirmed independently by a number of groups working in different collections of samples from different parts of the world. It's always the same story. So it's this pyrite type that is richest in gold. The Sun sedimentary, maybe early diagenetic pyrite, the one that grew on the sediment surface or in the sediment. If you go to the shales, we find a similar story. Now that's work done by Ross Large, and I'm just going to quote Ross Large in one of his papers. Gold was enriched in the Meso to Neo-Archean oceans several times above present values, just based on the global distribution of gold concentrations in pyrites of different age. Although the sentence is wrong because the gold wasn't enriched, it was the oceans that were enriched in the gold, but apart from this little semantic error, Ross Large made a very important point here. If you look into the shales, and that's largely the work by Glenn and Baila, we get the same story. 2.9 billion year old shales tend to be much richer in gold than all the other shales. So at around 2.9 billion years, there was something really special going on that led to a high concentration of gold in meteoric waters, but by the looks of it, even in the marine environment. So from all of this, we concluded a couple of years ago that this 2.9 billion year gold mega event could be explained by microbial gold fixation. So in other words, we have a hinterland with meteoric waters that are loaded with a gold sulfide complex, leaching gold out of the hinterland, granite greenstone terrains. We are leaching out no special high elevated gold values, just normal background gold concentrations. This gold is in dissolved form washed towards the coastal regions, where we have settings like this one here possibly. And in these kind of settings, we get the precipitation of gold on the surface of microbial mats, the first probably cyanobacteria that produced oxygen through photosynthesis. Then, of course, we have maybe a regressive event, and our microbial mats, well, they're very delicate structures. They would have been reworked by mechanical reprocessing of the sediment. That would have released the very fine-grained gold in these microbial surfaces, and this fine-grained gold would have then been the source for fine-grained placer gold further downstream. So effectively, our placer gold would have been directly derived from the mechanical reworking of these microbial mats in wetlands, near coastal wetlands. If we do a bit of a back of an envelope calculation, we can calculate how much gold we could fix by this process, and just on the order of magnitude, we could actually fix more than 1 million tons of gold per million years. Well, we have quite a few million years available for this, and so we could explain far more gold than that is known in all gold deposits in the world. I said it before, the Witwatersrand is not unique in terms of style of mineralization. We find similar conglomerates also on other continents. The Witwatersrand is unique in terms of its enormous gold endowment. Similar conglomerates I had the pleasure of looking at are in India, both on the Singhbum Craton in northeast as well as on the Darwa Craton in the southwest of India. They are probably older than 3 billion years. They are beautiful conglomerates, sedimentologically very similar to what we find in the Central Rand group, but the gold endowment is much, much, much lower than in the Witwatersrand. It's effectively not economic. And that sort of raises the question, why? What's the difference between these Indian examples and the Witwatersrand? One difference is the age. These Indian conglomerates, as far as we know at the moment, although I must admit the age control is not very good, but our current understanding is that these Indian conglomerates are a little bit older. They are older than 3 billion years. The Witwatersrand, the richest conglomerate in the Witwatersrand, are between 2.9 and 2.85 billion years. So what could be the reason that we don't have rich gold-bearing conglomerates that are older than 2.9 billion years? And I'm tempted to say that this might have something to do with climate. If you take the Witwatersrand, well, the West Rand group, why don't we have much gold in the West Rand group? There are conglomerates, not as many as in the Central Rand group, but there are conglomerates. And okay, they might have somewhat anomalous gold values, but by no means comparable to the Central Rand group. And the reason for this might be that we simply didn't have a good source, because one of the necessities, the requirements, remember, is deep chemical weathering of the hinterland. But during West Rand group times, it was probably pretty cold. We know this from the presence of glaciogenic diamictites in the West Rand group. We know this from the abundance of detrital feldspar, which is in strong contrast to the Central Rand group sediments, where we don't have any feldspar effectively. We know this from generally lower chemical indices of alteration in the West Rand group. So maybe it was just too cold, and it means chemical weathering was not intense enough to dissolve large amounts of gold at over a given period of time to be transported by the meteoric waters of the land surface. Maybe there was another problem, and that is that we didn't have good traps. In other words, we didn't have these microbial mats in those days. At least there is no evidence preserved from the West Rand group of carbon seams, to my knowledge. But we do have microbial remnants in these older rocks. The pictures I brought you here pictures of microbial remnants from conglomerates in India. They are probably about 3.2 billion years in age, so more or less the same as the ones from the Moodies group. But again, the Moodies group has got microbial mats, but doesn't have gold, at least not in the sedimentary environment. So I think it's a combination of climate and microbial mats, or the presence or absence of them in the right environments to trap the gold. And well, if none of these conditions have been met, then we don't have the source for fine-grained detrital placer gold further downstream. If you go to younger conglomerates, and again, we find examples of those all over the world. Here's just a sort of a compilation of reasonably well-known Archean and Paleoproterozoic conglomerates, most of which are gold-bearing, some of which are terribly rich in gold. And of course, those that are younger than the great oxidation event, they don't have detrital pyrite and uraninite anymore, but carry detrital iron oxides instead. So for these younger conglomerates, the source for the gold in those, that's easily explained. Because after 2.8 billion years, we have already orogenic deposits in the hinterland. We have in places evidence of gold derivation from volcanic massive sulfide deposits. But the most important probably is the older paleoplacers that have been reworked mechanically by resedimentation on various erosion surfaces. So for these younger gold deposits, we have plenty of sources, a great variety of sources, but remember, the overall gold endowment is not comparable anymore to the 2.9 billion year old conglomerates. So in summary, we can observe that for rocks that are older than 3 billion years, we have very little gold in them. And the reason for that is probably that we didn't have an efficient trap in the crust at that stage. And in conglomerates that are older than 3 billion years, we also didn't have a good source for whatever gold from whatever environment, because we also didn't have a source for orogenic gold. So orogenic, porphyry gold, and so on didn't really form prior to the onset of some kind of plate tectonic processes. Then the main conclusion, around 2.9 billion years, that was the gold mega event in Earth's history, when probably something like 90, 100,000 tons of gold were bound by microbes. Well, probably many, many more tons of gold were bound by microbes, but these 100,000 tons, that's what's probably left behind today. Immediately thereafter, this microbially fixed gold became reworked into placer gold, and this placer gold production became less and less and less effective over time. But from about 2.75 billion year onwards, we start to get orogenic gold. That, of course, required that we had already some subduction of some gold-bearing sediments. So maybe the first Mesoarchaean placers provided the first source for the gold that eventually became tectonically, hydrothermally, magmatically recycled to produce orogenic porphyry epithermal gold from about 2.75 billion years onwards. And last but not least, we can also state that all the younger gold deposits, the great variety of gold deposit types that the students amongst you have to learn in your economic geology classes, are effectively nothing else but recycling, repeated recycling of gold that became initially concentrated on the Earth's surface at around 2.9 billion years by this microbial activity. Well, I know I've taken far more time than I was originally given, but unfortunately we don't have the time now for a discussion. So those of you who have gained some interest in this topic, maybe through this talk, and if you want to learn more about this, I give you here a list of some of our recent publications on this topic. I would also like to misuse this opportunity to make a bit of an advertisement for our work, and that is just a few weeks ago, a new textbook came out, a textbook on mineralogy, Introduction to Minerals, Rocks and Mineral Deposits, by my predecessor here at the University of Würzburg, Martin Okrosch, and myself. This is the English version of a legendary textbook that has been on the German market for many, many years, but in an updated form. So if you are looking for a general textbook for your library, for your student classes, for whatever, then check out the Springer website. That's where the book appeared. Finally, I would like to thank you for listening. I would like to thank, of course, the bunch of companies that have sponsored in one way or the other some of the findings or the works that led to the findings are presented here to you. I would like to thank the Geological Society of South Africa for the invitation to present this talk here. And well, in the absence of a discussion time here now, I invite you, if you have any questions, comments, anything pertaining to this talk, please feel free to drop me an email. You've got here my email address. And yeah, I would love to receive your feedback. With that, I wish you all the best. Stay safe and healthy, and hopefully the next time again in analog form, in physical presence. Bye-bye.